Hello guys. So as we have discussed last time, so let us go deep in continuity and maybe today also I will not discuss, some concrete examples rather than I will do some important theorems or observations. I'm not sure. Let's see how it goes. And maybe if it will not be a very long video, then we can talk about, homeomorphisms also in this video in more detail or some examples. So, sorry, let us begin, okay? So, if you have noticed, I have given many exercises to you guys regarding continuous map. Like in last video, I guess I asked you to do composition of continuous functions as continuous, and similarly a few exercises I have given. So let me also begin with the exercise only. This kind of things you should able to prove on your own. And yeah, one exercise I have previously given you, that f from x to y is continuous if and only if inverse image of every basic open set is open, or if and only if inverse image of every sub-basic open set is open. Right? These kind of things I have given you. So let me begin from an exercise. So theorem. So it's an exercise for you guys. Maybe I will see if I prove some parts. Let's see. So let x and y be topological spaces and f from x to y is a map. Okay. Then following conditions are equivalent, or following are equivalent. So TFAE, following are equivalent. So what? Number one, f from x to y is continuous. Number two, so f inverse of capital F is closed in x if f is closed in where y. So basically, pullback of any inverse image of any closed set is closed. That's an equivalent condition. I think this you can deduce, very easily. So third, let me see what is third because I forgot, but it is in fact very important. So f of a closure is contained in f of a whole closure for each capital A sitting inside X. And this is one of the most important condition. We will encounter this in when we study first countable spaces. There's something called first countable spaces, and particularly this equivalent condition for continuity actually plays a crucial role there. Okay, and fourth, again I have to see, I don't remember these things. So F inverse B whole closure is sitting inside, I think, yeah. So where is B? You can naturally guess, right? For all B in Y, right? Okay. So I think I can leave this as exercise. So it's not very difficult. Like, okay, for example, let me show you one. So follow this chain. One implies two, two implies three, three implies four, four implies one, or anyhow you want to follow. So let's say proof Let me prove just say 2 implies 3. So to prove 2 implies 3, first observe that. Okay. So f of a closure, since it's a closed set, I think I have discussed about closures. Yeah, I have. So since this is closed in where? Y. So by 2, f inverse of f a closure, whole closure, is closed where, guys? It is closed where? It is closed in X. Now, observe. So there is a one crucial observation. What is that crucial observation? That A sits inside F inverse of FA whole closure. This you can check. Now tell me, what is A closure? Sorry, what is A closure? A closure is the smallest closed set containing A, right? By F inverse of FA closure is also a closed set containing A. So what should happen? A closure should sit inside F inverse of FA whole closure, right? That's what. Now, what this implies, F of A closure sits inside F of A whole closure. I hope this you got, and perhaps this is the most trickiest part. So what I've said, you observe, you have to prove it, okay? I'm not proving it. So, and rest, the whole proposition or theorem will follow similarly. But please always remember this property because this comes very handy in many situations. So I will give you when we will study about first countable spaces. All right, let us move further. I want you guys to give a definition. So you might have, sorry, I have a bit cold today. It's the weather of Pune. So, okay. So, okay. Yes. Let me give you a definition. And if you remember, when you have done real analysis, you started continuity at a point. So, does we have some similar analog in topological spaces also? Because how I have defined continuity of a function from x to y, right? But what about a point? Is there an analog and is there a result that f from x to y is continuous if and only if it is continuous at each point? So the answer is yes, it is true, and there is a analog. So definition. So this is just motivated from your epsilon delta definition only. Okay, let me write how you say f is continuous at x in A. Say f is a map from metric space xd to metric space ye. So if you remember, so what is the definition for each? Epsilon bigger than 0, there exists delta bigger than 0, such that what happens, guys? So whenever this d of x comma a is less than for some x, whenever the e of x comma is less than delta, this will implies what it will implies, guys? D of f a, sorry, yeah, fine, metric. So x is less than epsilon. So in other words, I'm just rewriting this condition. So x belongs to ball centered at A of radius delta with respect to the matrix T. If x is there, then fx is in ball in metric E. Sorry, by mistake I have written here D. Yes, such silly mistakes you might have, obviously observed. Fa of radius epsilon, right? So what is this actually? So if you apply F on this ball, you are actually inside this ball. So F of B, D, A delta, this actually sits inside B. So yeah, B F epsilon, sorry, F A comma epsilon, right? And vice versa also is true, right? Let me check. So if, yeah, vice versa is also true. So this is the condition. So what is this? So in other words, you have a open set around FA, then there is another open set around A such that the image of that open set is contained in the original open set around f of A in Y what you have chosen. So that's the precise definition. So what is the definition in topological spaces? And you can see it is equivalent to this definition of metric space. So f from x to y is continuous at say some c if for any open set say v contained in y and c is in y v f of c. So basically for any open set of y which contains f of c, there exists an open set say u suffix v in x such that f of u suffix v sits inside where, guys? It sits inside v. That's all. So, the same kind of definition it is. You can show that this is, equivalent. Open set, okay, just a second. Containing x, of course, that otherwise it doesn't make sense. Open set such that x is in, sorry, not x, c. C is in u suffix v. Okay, so this is what you have. Now, this is just motivated from that. It's your exercise. Exercise. Show above definition matches with definition of continuity at a point in metric spaces. You may have done this exercise, but you might not have written like this. So let me have a theorem then, which we expect. And yeah, this I want you guys to do on your own. Theorem is also exercise. So let f from x to y be a map. F is continuous if and only if f is continuous at x for all x in x. Oh, sorry. Okay, so for all x in x, if it is continuous, then it is continuous, and if it is continuous, then it is continuous at each point x. I hope you guys can do this. It's not very hard. Okay, let me do one part of it, which you may find bit hard. So let us do the converse. So what you have given, this condition that it is continuous at each point, and what you have to show that it is continuous. So what is the what you will assume? So let V contained in Y be open. What you have to show? To show F inverse of V is open. That's all. Right. So let us see. Just a second. Yeah. How we can do this. So definitely. Now you are talking about continuity at a point. So you have to take point, right? So let x belongs to V be arbitrary. Okay. Not V, F inverse V, huh? So what does this mean, guys? That is right. Now, fx is in V, right? Okay. And V is open in Y, right? So what is the definition you see? For any open set containing the point f of, that there is an open set, right? So definitely it depends upon this open set. Here my open set is V only for the point x, so it actually depends upon the point x only. So I will give the notation u suffix x. So since f is continuous, CTS I'm writing in short, please don't do in practice, at small x, there exists u suffix x which is open in x and it contains definitely x also. Okay, such that what will happen? F of u suffix x sits inside B, right? Or u suffix x sits inside F inverse of V. Is it fine? Tell me if there is any ambiguity. So, what you have done? You have x in ux, okay, and this inside F inverse Vx. This is for every x in F inverse V, right? Now the standard thing, take the union over x. So union singleton x in F inverse V is contained in where, guys? Union ux x in F inverse V. Do something click to your mind? Something similar to bases, right? There was a theorem regarding bases. Union of this, anytime you will see it is this only. And what is this? This is F inverse V. So what you get? F inverse of V is actually union U suffix x, x in F inverse V. Oh, UX are open in X. So, okay. So this union will be also open in X. So this implies F inverse of V is open in X. That's what you want, right? You wanted it. Yeah. So, one way I have proved and another way is quite simple. So you can try that. Okay, nice. So we have the analog of continuity at a point also in topological spaces, and that's how it is. And definitely it matches with the definition of continuous map on a space or on a set. On a space, I mean. Of course, you need topology here. Okay, very nice. So another very crucial thing I want to discuss I want to discuss with you guys is something called pasting lemma or gluing lemma. So I have a theorem, a pasting lemma. So a pasting lemma because there are several versions in different places and if you know categories. So in different categories we do have different versions of this lemma called pasting lemma or gluing lemma. This you might have seen. So let me uh, leave it as okay, maybe we can do proof, not leave it as exercise. Let me copy the statement properly. So X and Y are topological spaces that I'm not writing. So say you have X is equals to union of I is from 1 to say N, and these AIs are closed in X. Okay. Or what you can have is X is union of I equal to 1 to maybe I will write this with different color. So what we want to say is this also work. Or if X is union of U alpha, alpha in some index set where U alphas are open in X for every alpha. So either you can decompose your set as finitely many closed sets or as any collection of open sets. Both of the things are gonna work. Okay, so let me write the statement then. And say you have a you know continuous map. So for each I fi from ai to x are continuous. So similarly, you know, you can write the statement in blue color also. There is no change. Same statement, right? For each I, those are continuous. Okay. Now, there's one more condition. Fi, when you restrict this map, restriction, when you consider that map on some subset. So when you restrict this map on some AI intersection AJ and you restrict FJ also on AI intersection AJ, there has to be equal for all I not equal to j. I mean, if I equal to j doesn't matter, right? Similarly, the blue color statement would be f alpha restricted to u alpha intersection u beta is same as f beta restricted to u alpha intersection u beta. And this is for every alpha beta. No need to write also I not equal to j, doesn't matter. So, I mean, because for that it is obvious that will always happen. Okay, so this is what we have. Then, so what I will do, I will glue these functions. I will make a common functions using this. So then define f from x to, oh, I have written x here, guys. It can be any other space, okay, y. So define x to y as f of x is equals to fi of x if x belongs to ai. Okay? And what will be the in blue color? Can you write? And then the claim is then f from x to y is continuous. Okay, that's all. Similarly, in blue color. Fine. That's what you're gluing, gluing these functions, right? F is basically defined using these, AIs or UIs or U alphas. So I'm not gonna prove it. I will, give you an observation. Or maybe let's see. Okay. So proof. So the observation is, let me write the observation. So, okay, let's do for the closed set. So, okay, let us prove it. F contained in this is closed in where y. What you have to show F inverse of F is closed in X. So since I'm proving it for closed set, I'm using this closed definition. If I do it for open set, please show that inverse image of every open set is open. You can begin from closed set also, but you have to use that open set thing. So that is why, okay? Now, see, FIs from where to where? AI to are continuous, right? So whatever the will be the proof. Okay, okay, yeah, later. So what you have to show that this is easy. You can show is nothing but union from 1 to n fi inverse of f. So since these are continuous, so fi inverse of f, what is it? These are closed in ai. And ai are what? Closed in where? X. So what you will get is from these two conditions fi inverse of f, this is closed in X. Verify it. Okay, so what this implies? F inverse of F is also closed because finite union of closed set is closed, right? right? Okay, closed in X. That's what you have to show. So what will happen in the open set case? You will see this as this will be some union over, I'll find capital lambda and rest everything will follow similarly. The closed thing will be replaced by open thing and we know arbitrary union of open sets is open, right? So the thing is, there's a catch. So if you see the proof, in proof, if I ask you a question, if I replace these AIs, these are finitely many closed set. So question, what if this family I is from 1 to n, rep- is replaced by some, infinite family, for example, of closed sets in X. And the same hypothesis. So I will give you a homework. Show that above theorem does not hold. Okay, take an example, try to see. But in proof, you can observe the technique what we are proving. So if there is infinite union here, then infinite union of closed sets need not be closed, right? So that will be the probably, the problem. So I think this let me leave as exercise that why above theorem doesn't hold. So next question is, does it hold for some special family of closed sets? Okay, if it doesn't hold for, any family of closed sets which is not finite, then does it hold for something? Can I impose some condition on my family so that this result hold? So the answer is yes, and it's a very deep result. So definitely, at my time I didn't get it. I have read only. So there is something called locally finite families. So let me first define that definition. Locally finite families. Families. So this is very, very, very important at various places. One example I can give you when you study something called para compact spaces. When you study called something called integration on manifolds. So this is so important. So let us understand this definition properly, huh? Okay. Let X be a topological space and say AI, I in I, some index at I, be a family of subsets of X. We say capital I in I is locally finite if. See, we will justify the local word and the finite word. If for each X in X. So I'm taking a point, right? So something local is gonna come. Okay, there exists an open neighborhood. See locally. Open neighborhood or open set neighborhood U of X such that what will happen? So U intersection AI, this is non-empty. So local word is justified. Now I am justifying finite. In what sense finite? So is non-empty for all, or maybe let me write like this, empty for all but finitely many eyes. So what I'm saying, for every point there will be a neighborhood which will intersect with only or at most finitely many members of this family. So that's why finite. And local because it's a local property. At every point, there is a neighborhood satisfying something. And some people also call it, since I said neighborhood, so some people also call it neighborhood finite. Locally finite or neighborhood finite. Okay. So before answering, the final question, does it hold for some special family of closed sets? Let us have a result. So this is another, application of this locally finite families, and you will see encounter this again and again in when you study this differential geometry, topology, or calculus on manifolds. Whenever you deal with the integration, and then I don't want to disclose it now. Maybe someday I will. I mean, I don't know when I am gonna upload those lectures. I will upload it and I will use it. Okay. So what's the theorem? I forgot. Let me see the statement. Yeah. So let bracket I in I be a family of closed, no, be a locally finite family. Hey, you might be thinking that, oh, this is going on so abstract. Yeah, we will see examples, but this abstraction is important. That's what, it makes topology so beautiful. So topology definitely has abstraction. You cannot always, you have in most of, not, you have in some or many situations, pictures and all to understand things. But there are places when you cannot visualize, like for example, above R4 you cannot visualize. So there are places like that. So abstraction is very important. So I in I be a locally finite. Let me see if my locally spelling is correct. Does it need double L? Yeah. Finite family of closed subsets of X. Then if you or no need to, have closed subsets. I mean, it's unnecessary imposition. So just subsets of X. Subsets of X. Then if you see this union, see what is AI closure? AI closures are now closed sets, right? So this, arbitrary union of these kind of closed sets will become closed. Now I think, you can answer this question. I'm not gonna prove it. So this statement, you can easily observe if I take the locally finite family of closed sets, then closed sets, the closure will be same. So now you will have here in this union, infinity, and that infinite union will be closed. So, so you will be done, right? So remark, then we will prove it. This theorem, remark, gluing lemma or pasting lemma holds for, this is also an exercise. I have just verbally said you. So you have to verify it. Holds for locally finite family of closed sets. Number one. Let's have some more remarks. Number two. I mean, if you clearly see this finite family of subsets of X is always locally finite, right? Because there are only finitely many sets. Because I haven't given you any example, so I thought, let me give you this example. I mean, there can be, many other example. Okay, let me give you, say, no, I'm not giving now. I will give it later on, huh? One example we will encounter one or two. There can be many. So let's not go into locally finite families too much because I want you guys to observe more and more example. So another homework. So these all are homework. Construct a few example of locally finite families. Okay? Okay, one I can give you. It's sort of obvious, but yeah. So, for example, let X be a discrete space, means every set is open. Then we just consider this family of singletons, X in X. This is locally finite. You can verify this. For every X, you have just singleton X, which will intersect only one member singleton X, right? Or just if you are getting confused, take another point Y in X. Okay, you can say assume that for the fun that it's infinite cardinality. So take Y in X, singleton Y is open, and it intersect only one of this member in this, locally finite family. So it's a family of infinitely many sets, but it's locally finite. So you get it. A family can be infinite. Still, it can be locally finite. So it doesn't matter how many members are there in your family. If they are finite, then it is always locally finite, no discussions, right? But there are infinite families, so I have given you one example. Okay, so let's prove this green theorem. So what is the green theorem? If you have a locally finite family, take the closure of each and every member and their union, that will be closed in X. So this is a very beautiful proof. So let us do it. So proof. And then we will probably, stop this, section, session. Yeah, section I say sometime because so you see, these are the lectures I make. So wherever I write, it's section. So that's why I get confused. Okay. So how you show some set is open, you express it as union of open sets, right? So you have to show this is closed. So I will show its complement is open. So we will show X minus union I in I closure, say something, let's call it V, is open in X. And we will be done, right? So to show something is open, let's take a point inside it. Let X belongs to V. What it means, guys? X belongs to X minus union I in AI closure, right? Now, since X is in V, okay, and V is definitely inside X, so X is in X. And this family AI is locally finite, right? So what will happen, guys? So this implies there exists an open neighborhood U of small x, such that what will happen, guys? Such that U intersection AI is empty for all but finitely many i's. So assume where it is non-empty. Okay. So let's assume it. So hmm, okay. So say it is in some. What should I name? That's what I'm thinking. Okay. Say U intersection A ij is non-empty. Okay. Um, for j equal to some 1, 2, dot k. Okay. And U intersection AK is always empty for every k not equal to I suffix j. Right, that is what, the condition is. Is it fine? Okay. Now, let me think something we have to do. So let me, see the outline of proof, then I will prove it for you because, yeah. So we have one thing, see, we have, we have this thing. U intersection AK is empty, right? So this will implies U intersection AK closure will be empty for all K not equal to I suffix J. Is it fine? So why this will be non-empty? Sorry. Why this will be empty? You note that here you have, yeah, I think this is fine. So why this will be true, guys? Let's assume that this is non-empty. Okay. So say y belongs to U intersection AK closure. So what it implies, guys? So let us call this 1 because we haven't used it yet. So what this implies? So this implies y belongs to U. U is open, okay? Open in where? Um, your set X, and Y belongs to AK closure. But you know, what you know? X belongs to A closure if and only if every open neighborhood of X, this we have done, or I have given you as an exercise, intersects what? Capital A. So since Y is in AK closure, this implies U intersection AK is non-empty, which is a contradiction, right? Because you know that U intersection AK is empty. So what you are getting is, let me have, all everything together. So in short, first thing you have X we have taken in X minus U union and closure. Second thing, there is open neighborhood U of X such that what is the property? That U intersection Aij is non-empty for all j equal to 1 to some, what was that? K we have taken, N we have taken. So since I'm using K here, so I will write, something else. L, let's say L. Yeah, these are things, you should learn to write and correct it if you are doing some mistake. L. And apart from that, U intersection AK is empty. Basically, U intersection AK closure is empty for all K not equal to I suffix J. J is in 1 to N. Right? So you have this. Now, I will give you a very, very, very small exercise. Okay. Define. That is very easy using just these observations. Okay. So define. Let me think what to define, huh? Because it's it's a kind of tricky proof. That's why I'm taking time. So I have to think how to define it. So let us define V to be U intersection J is from 1 to L X minus A I J. Note that this is what? This is open. I want you to show number one, X belongs to V. Number two, what I want to show you is V intersection union AI closure. Or maybe let me make it a bit easy. AI closure is empty for every I. Okay. So if you show that, you will be done. Why? Because you will have this B and this is contained in what? And this is open, right? This is clear. These are closed sets. So complement will be open. Finite intersection of open set is open. So if you have this, so what you have? So X is in B. And this is contained in X minus union of AI closure. I in I. So this will implies for every X, now you can take union of all X's over union of AI closure. What you will get is X minus union I can be expressed as union of such V's, right? Containing X. So basically this is open. So this implies union I in I, AI closure is closed. So that's all. So you show these things, huh? Homework. It would be something similar analysis using what we have done above now, how we have come to the second point and first point. Just you have to use the properties. That's all. Write it carefully. You will be able to do. So I think this is like going pretty much long. So I will stop this lecture here and the plan for the next lecture might be examples of continuous functions. Yeah, I am telling you this is the plan from past two lectures, but yeah, we have done examples also. And this is like, kind of, this also gives you kind of class of examples if you apply these lemmas on various situations. Continuous functions, homeomorphisms, homeomorphism, open map, closed map. So yeah, this might seems to you be abstract, but yeah, that is what topology is. So you have to deal with sometimes, but it is this what we are doing is currently points at topology, right? So point is there, set is there, locally things are happening. So this is very important, and this version of gluing lemma is very important. And locally finite families in particular are most important, one of the most important objects. So yeah, thank you very much. I hope you like the video. So yeah, I have given you various exercises and I will be keep doing on, in the coming sessions also. So please try to solve it. If you have any doubts, you can always ask in comments. Thank you very much. Bye bye.